Alright, so now we are going to understand what are called similarity transformation. So let's look at what are called composition of maps. So I have two maps S and T. So I have vector space V, W and Z. I have got three vector space. Here the dimension is M, or I was writing N, I think, N here, M here and P here in different ways, whatever it is. I have a map here which is T, I have a map here which is S. I want to understand these. We also have a basis here A, ordered basis B, ordered basis C. So want to understand the map SOT which is from V to Z, alright. V has N and A here, this has P and C here. I want to look at the matrix SOT, this A and C. I want to understand what is this. Is that okay? This is what I want to do. What I know, since this is given to me, so I know what is the matrix of T. T of AB is given to me. What is the size of T of AB? Recall, since I am going to multiply by n here, so it will be an M cross n matrix, fine, so that it makes sense. Here it is going to be S from B to C, so it will be P cross M matrix, fine. Is that okay? So you can see that if I want to talk of matrix multiplication here, I need to do P cross M, M cross N, M has to cancel, so it has to be S of BC times T of AB. Alright. This is the way it has to be, because then only I can look at here P cross M, M cross N, this cancels out, I get P cross N, and this is what it should be, because this is P, I have to multiply by N, so this has to be a matrix of P cross N. So at least I can hope of thinking that they should be the same. Forget about matrix multiplication. At least the size wise, I can see that it makes sense for me, that I can go from these two different matrices to this. And observe here that S here, even though it is on the right, when I want to multiply it as a function, it comes on the left. It is SOT, that is the function that comes here. It is SOT. First apply T and then S. First apply T and then S. Is that okay? So therefore you get S in the beginning and T at the later stage. Is that okay? So SOT and SOT is here also together with you, fine. So how do I get it? Let's try that out. So what you have to recall here to understand everything is, everything here is with respect to N or A, here it is with respect to B, S, alright. So let's try to understand things in a nice way, fine. So just let me try it out here itself. So I have T of AB, if I want to look at T of AB, T of AB will look like T of V1, T of V2, T of Vn. So this has basis, that is V1, V2, Vn, I have this basis, fine. Each of them have to be evaluated with respect to B, because B is the ordered basis of the codomain, I have to write like this. Fine. Now, what is TV1? I want to understand what is TV1. TV1 is an element of W, everything is nice with us, no problem. But I can also apply S to it. Now, if I apply S to this, fine, because TV1 is an element of W, this belongs to W. So I can apply this, fine. If I apply this, then this is an element of Z now, so this becomes an element of Z. Alright, so I wrote Z as a matrix, so let me, I think you will get confused. So V, W and say, because Z is something else that we have been looking at, Z, just Z, alright, not double Z, alright, because double Z was for integers. Alright, so let me just write Z here, fine. So here also let it be just Z here, fine. So if I am writing this here, it means that I am supposed to look at, see, S here, and this is some vector. I don't know what that vector is, but it is some vector, some element of W, fine. So what this part tells me, this matrix part tells me that this is nothing but the matrix of X. So this is basically equal to, with respect to C, if I want to look at, it is S from, go from B to C, all right, and then whatever this is, T of V1, you are supposed to do with respect to B. Is that okay? So recall here. So here also, if you want to see, recall that T of V with respect to B is an element of this, is an element of W. So this is equal to T of AB times V, but V is with respect to the basis of the domain, fine. So this is, be very careful here, that what you are writing is should make sense for you, all right. So T of V is an element of W. Since it is an element of W, it has to be, its coordinates have to be computed with respect to B. So you write B here. V is an element of V, so it has to be computed with respect to A, so you compute it. And now this A and this A needs to be cancelled out to be left out with B, all right, fine. Similarly here also, if you see here, this B and this B has to be cancelled out. You are evaluating at A and getting final answer at C. Is that okay? So this is where you have to understand. So let's try to write it nicely with whatever understanding I have here. So if I want to compute this matrix, so this by definition is I have to look at SOT of V1, fine, and finally SOT of Vn. I have to compute this, fine. So this matrix is going to be this matrix, but this has to be evaluated with respect to C because C is here. So this has to be evaluated with respect to C. Is that okay? So this by definition is equal to S of TV1, this with respect to C, so on, S of TVN with respect to C. This is equal to, now look at this definition here for you. I can replace this by S of BC times T of V1, but with respect to the basis B here, fine. So I have this, I will go on. Finally here also it will be S of BC, fine. Again T of Vn will come into play, and this is with respect to B. This is what I have. Now this is a matrix, this is a matrix. By matrix product, this thing will come outside, S of BC will come out. I will be left out with TV1 of B till TVn of B, and recall that this basis is nothing but TAB matrix. So this is equal to the matrix T of, so I have already S of BC, and this matrix is T of AB. So I have got the matrix. Is that okay? So the matrix is very simple. I don't want you to remember it, and I am not going to ask a single question on this, but you should know that they come from matrix multiplication. Everything made sense because of matrix multiplication, all right. Or you can say that if you want to define it like this, the matrix multiplication has to be proceeded accordingly, fine. So the idea of matrix multiplication has indeed come from understanding composition of functions as such, all right. So from here I want to get one thing which will be useful for us afterwards, is trying to understand what is called two things. T of, if I want to go from A to A, so I have mapped T from V to V. There is a basis A here, there is a basis V here, and I want to understand how are these two related, all right. So in the previous class we saw this, but we saw it for, I defined T of S is equal to Sx, and from there we saw that there is B inverse A which comes into play, and from there we went and understood these things, all right. I want to understand it in a different way now, using directly, because there it was Rn, and therefore I had matrix already with me. But when I have just any V here, I may not get Rn. I can think of them as isomorphic to Rn and then build a whole idea. But in general, if I want to do it, how should I do it? Fine. So again, I am going to make a diagram the way I made a diagram here. All right, I just made a diagram like this. Fine. So there will be a similar diagram here that I am going to do. There will be a lot of confusion. Just bear with me, because I am not going to ask you any question on that, but you should know how to do it. There will be some questions where you have to compute T of AA and T of BB. That's all. And check that everything is nice. But this diagram you need to understand, because such diagrams are always there in mathematics. And whenever you study some books, you may have to come across that. So let's try to understand. I have a V here. Fine. This V comes with a dimension n, and it comes with an ordered basis. Fine. Again V, n is there, I have A. I have the map T here. Is that okay? So this T will give me A and A with me. Fine. Similarly, now I have V, dimension is the same, but now I have a different ordered basis here with me. Since I have a different order basis, so this map T will give me a matrix B here. Fine. I want to relate these two. If I want to relate these two, what I will do is that I will have a map which is the identity map here, also the identity map here. Fine. So that everything is, I have been writing it as ID. So let's try to understand that composition of functions makes sense, and then we will look at how do I get the matrix out of it. Fine. Which will be helpful to us. So take any element here, say x belonging to V. So I am going to look at this map, this composition of map. This composition is T is coming here. So T composed with identity. Fine. This map will be identity is coming here. So it will be identity composed with T. So there are two different maps here. Fine. So what is T O identity of x will be equal to T of identity of x, but the identity of x is x itself, so it is T of x itself, as identity of x is x for all x belonging to V. All right. If I want to look at identity composed with T of x, then this is equal to identity of Tx. But what is Tx? Tx is an element of V itself. Since Tx is an element of V itself and identity does not do anything to it, it will give me Tx itself. All right. So what we see is that these two functions, all right, composition of functions, they behave same on every element of the domain. All right. So what we are seeing is that I have got two functions. One is T composed with identity, the other is identity composed with T. They behave the same on every element of the domain. Since they behave the same on every element of the domain, so they are same. All right. So TO identity is equal to identity composed with T, as both the functions, both the composite functions take the value, take the same value, take the same value Tx for all x belonging to V. Is that okay? So they are same. So therefore we should be able to look at their matrices. All right. So if I look at this matrix, TO identity, fine. This matrix is coming from starting with A, the domain is A, and the final thing is B here. So I need to compute this matrix. Is that okay? So what we have learnt here, recall, in the previous, when we went, all right, T is coming on the left, so it will be T which will come here, all right, and then identity will come here. Is that okay? Now look at identity. Identity is a map from A to B, so it will go from A to B, and this T is from B to B itself. Fine. So this part gives me this matrix. Fine. What about this part? Identity composed with T. This is also a map from A to B itself. So A to B itself. identity is coming on the left, so there will be identity here, and there will be a T here. This is what we had learned, that if identity is on the left, the matrix of identity will come on the left. So this will be identity is going from A to B, so it will be from A to B, and T is going from A to A, so it is from A to A that you are looking at. Fine. So what we see here is that these two maps are same, so their evaluation at domain and codomain will be the same. So this will imply that TO identity of this will be same as identity composed with T of this, and this will imply that, just write down the matrices here, TO identity is T of BB times identity of AB. This is same as identity of AB times T of AA. Fine. And therefore what I get is that this implies T of BB is equal to, just multiply here on the right, so identity of AB, T of AA, identity of AB whole inverse. All right. So again it is similar to what we had obtained earlier. Here also identity will be the same here, so you get the matrix B inverse A coming into play, or A inverse B. Find out whether it is A inverse B or B inverse A. For clarity, just try it out yourself, do the computation, and you can see that everything is nice. All right. So what we are saying is that when I go from one basis, so understand this A is one basis, B is another basis. All right. So if I am going from one basis to another basis, so given a map T, then going from one ordered basis to another ordered basis requires us to multiply by an invertible matrix. All right. So I am not just multiplying with a quote mark here, because I am multiplying on the left and on the right, both the sides. All right. And on one side it is invertible, the other side it is the inverse of that itself. Is that okay? So there is this definition I would like to write for you. So there, if you look at TAA is n cross n, T of BB is also n cross n, all of them are n cross n matrices, so everything makes sense, definition. So let A and B be two n cross n matrices, then A and B are said to be similar if there exists an invertible matrix S such that B is equal to S A S inverse. All right. So it is similar to that. Here it was identity of AB, and here it was AB inverse. All right. Fine. So it is the same thing. I have changed it in the language of matrices now, because now ordered basis is not there. So recall, understand, there will be at most one question on 2 cross 2 only, TAA, TBB. You may have to compute them, fine, and verify that everything is nice. Nothing more than that. So just take some examples, practice it, fine. What will be more important is looking at this, that when are the two matrices similar. So this will be the crux of the question. When can I say two matrices are similar? all right. And as I said in the aim of this lectures, that the main aim of the lecture was to understand these. They will come through eigenvalues, eigenvectors, so I would like you to understand them. Also, we need to understand them basically because given a matrix, we need to understand what are the transformations, what are the ways we can do so that I get a matrix in the nice form. So let me take one example here to show you the importance of this example. All right. So let me take a matrix A as, I am going to take a very easy example, 2 1 1, 1 2 1, 1 1 2. All right, it's a very nice matrix, symmetric, everything is nice about this. You can try that out yourself. I will not talk about it, what are the nice things about it. Very nice matrix. Fine, at least you can see that it is symmetric. Fine, there are a lot of nice things about this matrix, I will not get into it. What I would like you to see that A times multiplied by 1 1 1, all right, you get it as 2 plus 1, that is 4, times 1 1 1, you can see that nicely. A times this 1 minus 1 0, look at this, this will give you 2 minus 1 is 1, 1 minus 2 is minus 1, 1 minus 1 is 0, fine. Similarly, A times 1 0 minus 1 will give you 1 0 minus 1. I would like you to check it yourself, fine. So therefore, what I see here is that A times this matrix, A times 1 1 1, 1 minus 1 0, 1 0 minus 1, all right. This is same as A times 1 1 1, A times 1 minus 1 0, A times 1 0 minus 1, which is same as 4 times 1 1 1, 1 minus 1 0, so it is 1 is here, and 1 times 1 0 minus 1. So I can write it as, see, 4 is there, 1 is there, 1 is here, all right. So they are being multiplied to the columns. Since I am multiplying to the column, it has to be on the right. So this thing I can just write it as it is 1 1 1, 1 minus 1 0, 1 0 minus 1. 4 will come because I am multiplying 4 to the first column, 1 is being multiplied to the second column, again 1 is multiplied to the third column. So A times this is same as this, is that okay? So if I am writing this matrix as S for me, fine, then I do get that A is, this is same as this, S times 4 0 0, 0 1 0, 0 0 1 times S inverse. Fine. So even though this matrix A, the starting matrix A was very nice, it was symmetrical, what I would like to say is that the matrix that I have got now, this matrix B, which is nothing but a diagonal matrix, is even better in the sense that I know that I just have to multiply by 4, 1 and 1, fine, and all the calculation, whether it is determinant, trace or anything that you can think of, solving system of equations, everything is very easy as per as this matrix, this diagonal matrix is concerned, all right. So the idea will be, when you come to eigenvalues, eigenvectors, to come back to these ideas and try to get matrices which has this nice property that I can make them diagonal, fine. Further, one thing more I would like to point out here, that if I want to understand, so let us see, I want to understand x, y, z times 2 1 1 1 2 1 1 1 2 times x y z is equal to set 10. I want to look at this system, all x y z in R3 such that this happens, all right. So you can see that this will give me some sort of quadric, all right. For example, it will give me 2x square plus 2y square plus 2z square plus 2xy plus 2yz plus 2xz is equal to 10, all right. So 2 can cancel out and then I can proceed. What does this represent? So the question is that, what is this quadratic? What is this quadric in R3? Is it a paraboloid? Is it a hyperboloid? Is it a sphere? All right, or is it a ellipsoid? So what is this? That's the question. All right. So here I would like you to see here that there is a 4 here, 1 here, and 1 here. It means that, and because of this 1, 1, and this matrix, I can easily write that this is same as, forget about the constant that I'll have to compute, but otherwise you can try to see that after some calculation it will turn out to be 4 times x plus y plus z upon root 3 whole square plus something coming from here which is x minus y upon root 2 whole square plus, I will do something to this, I will have to make some changes here and then change it to something like 1 minus 1, sorry 1 1, so that this is perpendicular to this, and minus 2, if I do it then this is perpendicular, this is, so I will have to do this. So it will be x plus y minus 2z upon root under 6 whole square will be equal to this. All right. So this tells me that I have got some things here. This one, so this vector is 1 1 1. This vector corresponds to 1 minus 1 0. This corresponds to the vector 1 1 minus 2. You can see that these 3 vectors are perpendicular to each other. All right, and hence they will form some sort of, in place of x y z axis, 3 axes, I have another set of 3 axes which are perpendicular, and therefore I have got the axis of the ellipsoid with me. All right. Since there is a 4 here, 1 here, 1 here with positive signs, I am getting ellipsoid. If I had got 1 negative, I would got a paraboloid, sorry, hyperboloid with 1 sheet. If I had 2 minuses here, I would have got hyperboloid with 2 sheets, and so on. Is that okay? So we will come back to these studies when we come to eigenvalues, eigenvectors. There we will try to understand when we can get matrices, and then this part of quadrics we will look at also 2 dimensions, so that we have a better understanding of things. That will again come when we come towards the end of the class. Fine. So this finishes our linear transformation for the time being. What we will be doing it in the next class is looking at what are called inner product spaces and build up on those ideas, so that we can talk of perpendicularity. All right. So here if you see, I had used the word of perpendicular here because 1 1 1 is perpendicular to 1 1 minus 1. So in this figure this is perpendicular to this is also perpendicular to this, but these two are not perpendicular. These 2 vectors are not perpendicular. All right. So what we want is a way to do perpendicularity. So I got this vector here. If you see, this vector is perpendicular to this one. This is also perpendicular to this one. All right, fine. So the next class we are going to understand when can I make something perpendicular. So we will start with not the dot product. So we will have a definition of inner product, but that will come from dot product itself. We will try to do everything in the general setup, but whenever we come to Rn or matrices or some things which are useful to us, it will be the standard dot product. All right. So you don't have to worry about it, but we should know that how do we compute inner products, how do you define new inner products. All right. So that's all for now. Thank you.